Pleasure to have Justin speaking on chiral algebras and FLE at the critical level.
Hey, I spoke in the theory seminar yesterday. I had time to prepare for this properly, so it's pretty interesting. So I'll start by talking about chiral algebras. So these are some objects that are maybe kind of more geometric flavor than vertex algebras. And the goal of the first part of the talk is going to be to talk about define chiral algebras, talk about them a little bit, discuss how to construct chiral algebras from vertex algebras and which chiral algebras arise in this way, and then talk a little bit about factorization algebras, which are an alternate different way of thinking about chiral algebras. It's sort of even more geometric. Okay. So f fix a smooth curve x. So a chiral algebra is something that so this business about vertex algebras, we're always talking about power series. It's really something that occurs on takes place on the disk, formal disk, or powers of a formal disk, or something like that. Whereas chiral algebras sort of exist over a global curve. So we have the decomposition of the square of the curve into the diagonal and the complement of the diagonal. And what I want to do first is define the notion of a chiral pairing. So let's say, I'm going to rely on the notion of D-module. It's appeared so many times in this seminar before, although maybe not in this quarter, but I'll kind of assume people have had some exposure to it. For a lot of purposes, it's enough to just know that it's some sheaf theory, but I will kind of engage with it a little bit more than that, and I'll try to kind of say some words of guidance as I go along. So say I have these three D modules, M1, M2, and N. Then I can talk about chiral pairings. Certain kind of pairing from 1, M2 to N. And by definition, the chiral pairing, this form is a morphism of D modules on X squared from following D module J lower star J upper star of M1 box times M2. So the source here, J lower star and J upper star behave very much like they do for quasi-coherent sheaves. Like in particular, D modules are quasi-coherent sheaves of the flat connection, and these functors are just given by the usual formula on the level of quasi-coherent sheaves. And you equip them with the connection in kind of the only way you could. And the target, so I'm going to write delta Durham lower star N. Okay, so this one is maybe a little bit less obvious. Again, if you haven't thought much about D modules, this one is a little bit less familiar of an object. So there's this operation of Durham push forward, and it is the natural direct image for D modules, but it's not given by the kind of usual formula for direct image at the level of quasi-coherent sheaves. It's something a bit more complicated. Okay, so we'll talk about this a little bit more, but in particular, like this, how do you say? It's sort of much bigger than the kind of quasi-coherent direct image, because somehow you have to allow not just kind of say this. If I took kind of the usual direct image of quasi-coherent sheaves, I wouldn't be able to differentiate sections, and so this thing is sort of necessarily larger. Okay, but in any case, there is such a thing. Again, we'll see a little bit later more explicitly what exactly this is. But this is the definition of a chiral pairing. And more generally, I can consider kind of in-area operations. Right, sort of clear how to do this. It'll be a certain morphism on x to the n. And so this defines what's called a pseudo tensor structure. And there's some axiomatics here, but it's sort of easy to imagine how this works. So it's not literally a tensor product, but what it is specifying sort of in-area operations for every n, and then there'll be kind of natural composition operations, right? So I guess there's sort of two additional pieces of structure here. So there's, first of all, there's symmetric group action on these things, so I can kind of interchange the indices. And then also there's some natural composition operations. So if I have an in-area operation, and then I have some operations valued in M1 through Mn with their own arities, right? I can compose those to get another operation valued in N. So this allows us to define chiral algebras, or more specifically, non-unital chiral algebras. On the curve X, just to be Lie algebras with respect to this pseudo tensor structure. So it's a D module on X. It has a Lie algebra structure with respect to this pseudo tensor structure. So these pseudo tensor structure is exactly the sort of thing that allows you to define commutative algebras, Lie algebras, things of that nature. And so a little bit more explicitly, I have a D module A. And the B bracket, right, is an operation, binary operation, this kind of shape. Okay, and then it's required to satisfy skew symmetry, which uses that kind of transposition action, right, on binary operations, and then Jacobi identity, which is some identity that takes place on x cubed. Okay, so certainly you could write down these things in an ad hoc way, but this pseudo tensor structure is kind of a nice way to formalize it. Okay, question about the definition. Okay, so that's some definition. Let me give an example. And so here's where we're very likely going to get confused about two things. One, shifts, and two, kind of twists by canonical bundle. So we've run into this before in the seminar, so I'll try to make it clear what I'm talking about. So I'm going to define a chiral algebra structure on this object. Okay, so what exactly am I talking about here? Well, the formula as I've written it, this omega x, I'm talking about really the canonical bundle, the canonical line bundle on the curve. It's natural structure of a right D module. Okay. So if you wanted to think about it as a left D module instead, I would maybe write it as like O of x or something like that, but for various reasons, I'm going to write it in this form. And then why the shift? Because really, I want omega x to have this property that it's dualizing, or canonical sheaf should have the property that it's sort of variant under Schritt pullbacks, right? If I Schritt pull omega, I should get omega. And in order for that to work, right, this thing actually lives in cohomological degree -1. So I place this shift to put it in cohomological degree 0. But again, it sort of is just as a plain quasi-coherent sheaf, like in the kind of right D module picture, it really is just this line bundle of one forms. Okay. Right. So we have a exact triangle the sort of Cousin exact triangle on x squared that I get by taking the kind of dualizing complex on x squared and then using this decomposition of x squared into the diagonal of its complement. There's always this kind of exact triangle, right? For like any d modulo on x squared, I can write this exact triangle. And so this is why and these cohomological shifts will get confusing, but I really want omega to live in, like omega x squared will live in actually in cohomological degree -2. And so if I use that normalization, then this is really just delta Durand lower star of omega x, because like I said, the point of omega is that it pulls back, it pulls back like this. So then I can rotate this exact triangle and I get a map from j lower star j upper star of omega x squared to delta Durand lower star of omega x shifted by 1. And then if I shift the whole thing by -2, oh, let me write it like this. Yeah, sorry, shift the whole thing by -2. I get a chiral bracket chiral binary operation on this omega x shifted by -1. Great, shifts work out. So we've gotten confused about this before. This works. Okay. And then from there, one has to check that it satisfies skew symmetry and the Jacobi identity. Skew symmetry comes from the fact that omega of x squared itself is invariant under transposition of the coordinates, and that kind of becomes skew symmetry because of this shift. And then Jacobi identity this thing follows from exactness of the Cousin resolution, or Cousin complex sort of omega of x cubed with respect to the incidence varieties inside of x cubed. Okay, so if you sort of write down this, there'll be some Cousin resolution, or you can write it as a complex. And if you, I think it's, yeah, exactness at one of the steps will exactly, if you kind of write down what that exactness says, it'll exactly produce. Okay, things about this example.
Our algebra, you don't use x as a curve. It can, like the same definition works for any x, like a formal disk or.
No, I'm definitely using the fact that it's a global curve. I mean, I don't know what
just in the definition.
I don't know what a D module on the formal disk is.
J upper.
Yeah, I mean, this whole notion of chiral operation, right, was very much using the fact that I have like an actual curve. It'd be great if you could say it just on a disk, but I don't know how to do it.
Oh, so where do we use that it's a curve?
Decomposition in.
You have to.
Like just from the very beginning, it's a D module on X. Yeah. What is a D module on the formal disk?
Well, okay, if it's like some, sure, but you don't need X as a curve. You can say like D module any variety.
Yeah, although, yeah, it does make sense on any variety technically.
But we only ever consider curves.
Yeah, we only ever consider curves, and
okay.
Yeah. Yeah, if you look in this paper by Francis and Gatesquare, which I'll reference again later, they do things on higher dimensional varieties. Yeah, I guess so. What happens for higher dimensional varieties is that there will be no kind of classical chiral algebras. They'll sort of inherently necessarily be derived because these shifts won't work out. Right. So it's kind of important here that X is one dimensional for this example to work out nicely. Yeah. Okay. Now, I can define a unital chiral algebra. So I guess from now on, they'll be unital by default. It's kind of a funny thing because the chiral algebra is a kind of a Lie algebra, and like certainly doesn't usually make sense to talk about unital Lie algebras, right? But reasons that I'll explain later, there is such a thing as a unit for a chiral algebra. So it's is a non-unital chiral algebra A equipped with morphism of chiral algebras from this example that I just explained, right? Such that, so there needs to be some compatibility between some kind of unit axiom, right? Compatibility between this map and the chiral bracket. It's going to look as follows. Consider this thing. Okay, use the unit map in the first coordinate. And then apply the chiral bracket. Okay, and I require that this equals boundary map in the exact triangle as follows. So sorry, I don't want the shift here. Shifts. Okay, so I apply the Poisson resolution to omega x box times A. Okay, and this is, and because of my choice of normalization, this for omega, this is actually just delta Dirichlet star of A. Okay, right, so when I rotate this exact triangle, I get a map exactly as such, right? Taking into account the shift. I want that this map equals the boundary map of this exact triangle. So that's the unitality axiom. It's a little bit opaque, like I said, which you should kind of expect because having a unit for a Lie algebra structure is a weird thing to begin with. And I'll explain that chiral algebras are kind of secretly equivalent to something called factorization algebra, already mentioned. And these are going to be some kind of associative or even commutative algebras where having a unit does make sense. So somehow this is really because these things are actually equivalent to some kind of commutative algebras. So it's the only reason that having a unital structure, if that makes sense.
Every Lie algebra.
Sorry?
In terms of that equivalence, every Lie algebra is equivalent to a co-commutative call. Usual duality works.
Well, causal duality isn't usually an equivalence, right? And yeah, maybe you can say something in other cases as well, but and somehow, right. Yeah, and in any case, it's something that again, for me, the explanation for why there is such a notion is because of causal duality. Okay. Questions? Other questions about definition? Okay, great. So I've defined unital chiral algebras. I gave one kind of uninteresting.
But it's actually like, why do you want this map to be the boundary? What does that mean?
Again, I think once I explain the equivalence with factorization algebras, right, they'll be kind of equivalent to these things called factorization algebras, which are a certain kind of commutative algebra essentially. And unitality, this unitality will exactly correspond to the corresponding factorization algebra being unital. And again, it has to do with, yeah, again, this example, right, already looks like the kind of thing that doesn't look very much like a Lie bracket somehow. It is technically, but say anything else more enlightening than that. Questions? Okay, so again, I gave one example of a chiral algebra, not the most interesting one. So to produce more examples of chiral algebras, I'll explain another way to produce examples later, but kind of to stay in keeping with the theme of this seminar, I'm going to explain how to produce chiral algebras from vertex algebras. So you can think of these things as being somehow like a coordinate free and also kind of more global version of vertex algebras. Okay, so some notation. I'll write odd underline of O for the group. Okay, so I can help myself here. So it's kind of a fancy object maybe, but it's actually like a pretty concrete thing. I'll explain what I mean. So the group n scheme of continuous automorphisms of O, which we used this notation before, is just power series. Okay, so there's some kind of naive automorphism group of this thing, and if you just look at it, you will see immediately that it's naturally like a pro-algebraic group. But in fact, we want to be a little bit more careful and really consider this thing as like a group valued functor on commutative group. So it's as a functor of points, okay, it's going to be maps from a test affine scheme spec of R into this automorphism group is going to be the group of continuous R algebra automorphisms of R double bracket C. And this makes sense for any commutative C algebra R. Okay. And so again, the kind of more naive thing that you would probably write down if you, were not thinking super carefully in terms of scheme theory would be the sort of underlying reduced group of this thing, but it has some interesting non-reduced structure as well, which is why I want to write it this way. So namely, if I have such an automorphism, okay, well, the variable C goes to some other power series, right? And here, A0 has to be, sorry, the more obvious condition is that A1 has to be a unit. Okay, and then the interesting thing that happens again when I allow kind of arbitrary test schemes is that A0 in fact can be non-zero, but it has to be nilpotent. So this is what I meant, if you only consider the kind of underlying reduced thing, you won't see this phenomenon, right? So I can in fact identify, points of this automorphism group with just certain power series of this form, and the group law will be given by composition. So the Lie algebra of this thing is also kind of familiar. It's the algebra of derivations, or I should say continuous derivations, the ring of power series. It looks like rank 1 free module generated by the operator of differentiation with respect to Z. We talked about this Virasoro algebra before, right? It came up already. So there's some kind of standard notation associated with this thing. the Virasoro algebra is a certain central extension of this thing, or maybe the thing for Laurent series rather, but in any case, there's some standard notation for the generators. This thing has a topological basis. The elements are traditionally written ln, normalization, for some reason, minus e to the n plus 1, lz. Again, for the disk specifically, the condition would then be n is greater than or equal to minus 1. And this gives like a topological basis for derivations of O. Questions about this? So this is all kind of set up. Yeah, so maybe calling it a group in scheme is like a little bit too fancy or something. It's a formal scheme, really. I mean, again, if I impose the condition A0 equals 0, or equivalently consider the reduced locus, it's going to be a extension of GM by something that's like pro-unipotent, right? There's like an extension of a bunch of copies of GAs corresponding to the coefficients n for n greater than 1. And then n equals 1 is going to give me a copy of GM. And then finally, n equals 0 is going to be a copy of the formal completion of GA 0. So it has this kind of formal direction. And what's left over is this pro-algebraic group that's like semi-direct product of GM with this thing. More or less solvable. All right, so now what kind of vertex algebras give rise to chiral algebras? I actually need a little bit of extra structure in order to do this. So structure is kind of an awkward name, quasi-conformal. By the way, the reference for all of this is Frenkel and Benz V. I'm referring to that a lot, right? So it probably kind of goes without saying, but more details, and in particular to see why this is called quasi-conformal. It really is a generalization of something called conformal that I won't have anything to say about. Look there. So a quasi-conformal structure on a vertex algebra V is first of all an action of the Lie algebra of derivations of O on V. And let me say on the vector space V, the underlying vector space. So there will be a compatibility, of course, with the vertex algebra structure, but it's not super obvious what it is, so I'm about to write that. Conditions. So condition 1 is that the action is integrable, so it exponentiates to an action of this automorphism group. So I could have first just specified the quasi-conformal structure by saying this group acts, but I guess the action of the Lie algebra is a little bit more concrete. I just have these operators Ln. Now I'll say in a second, like more explicitly, what this integrability condition amounts to, but just abstractly, that's the condition. Condition 2 is that L minus 1, which remember is minus del Z, acts by T, translation operator. Okay. And then condition 3 is something pretty complicated. So this is the compatibility with the vertex algebra structure, with the, I should say, the state field correspondence. So for any n greater than or equal to 1 and any state vector V, we have the following identity. So big formula. Okay, I have this bracket. Makes sense. It's going to be a Laurent series in W, I guess. And condition is that it has the following expression. Sorry, this is an N. So here I'm using the action of the algebra of derivations on V, right? So that for this expression to make sense. Okay, this is the identity. You're probably going to ask me like where this comes from, and I'm going to say I look at Franklin-Minsky because it's really, I mean, again, this is just sort of the correct compatibility, okay, of this action with the vertex algebra structure, with the state field correspondence. They give some justification by, again, first introducing this notion of conformal vertex algebra, which is like vertex algebra with an action of the Virasoro algebra satisfying some other conditions, which is something that, you know, you're interested in for other reasons. And then for a conformal vertex algebra, you can prove this identity. Okay, and then they say this generalization quasi-conformal, actually, if we just assume this identity, then we can do most of the same things that we could do with conformal vertex algebras. And in particular, we're going to be able to construct chiral algebras from these things. Okay. Does anybody else have something enlightening to say about this identity? Because
what does it say for n equals -1?
Question. For n equals -1, I would kind of expect it to reduce to 2. Right?
If it's a translation operator, then it's just derivative. That's it. That's the axiom. One of the axioms.
So you're acting like this.
Derivative with respect to that of the field corresponding to A, and you don't you verify also L0 acts as a grading operator, like.
Well, that's kind of part of 1.
Oh, sure.
But again, does 3 for n equals -1 specialize to 2, or at least imply it?
Sure, but
It should, right?
no, but you're taking the commutator of 2 with respect to a field.
Yes, the action.
One of the axioms. Times y over t.
Yeah.
It's
I think we combine with that. It follows from 3 at least, right? Yeah.
On the right hand side, you have like this infinite sum.
So maybe 2 is actually redundant given 3 for n equals -1, but writing.
Okay.
Yeah. Okay. Okay. Say something more helpful, but this. And then, yeah, let me say explicitly what condition 1 amounts to in terms of the actions operators ln. So 1 is equivalent to a combination of 2 conditions that I'll call 1a and 1b. So 1a says that L0, which remember is -z LC, acts semi-simply with integral eigenvalues. Remember, L0 spans the tangent space of the copy of GM inside of the automorphism group. So this is precisely the condition for that to integrate, right? And 1b is going to be on the remaining operators for, I guess, in strictly positive. So we call air sub 0 of O thing kind of topologically spanned by the Ln for positive n. or yeah, positive n. So the condition is this subalgebra, meaning all of the ln's for n positive, acts locally nilpotent. What? There's 0 or plus. I regret this notation choice. Hey.
The plus is when you take z square.
Okay. Sorry, let me just see if it's consistent with what I write later. It's supposed to be called 0. Okay, and then again, this is just this is the Lie algebra of the corresponding piece inside of out of O is pro-unipotent, and so the condition for it to integrate is just the Lie algebra acts locally nilpotently. Okay. Again, the condition that kind of the action of L-1 integrates is an empty condition because that part of the automorphism group is formal, so integrability is automatic. You do require that it acts by translation operator. Okay. Questions? Okay, so that's the notion of being quasi-conformal. So now, main example for this seminar is the Kac-Moody vertex algebra. So for level kappa, semi-simple Lie algebra G, we have this Kac-Moody vertex algebra. Okay. And I think it's not too difficult to kind of write down an action of this algebra of derivations if you think about it. So let me just refer you to Franklin-Benz V. So this one has a natural quasi-conformal structure. This is Franklin-Benz V example 649. Okay, so again, writing down the action of derivations is not that crazy, but the part that I for sure do not understand is the proof of this condition 3. So what they actually do is they prove that for non-critical level, this thing is actually conformal, so it has this kind of stronger property. And again, this looks a bit different, but they prove this specifically for non-critical level. And then they basically show that this identity at non-critical level implies this identity at critical level. Some kind of type argument. So
I think the answer to the question is that the bracket should be after W1. Thing should have n plus 1 terms. -1 dot dot dot.
sorry, say it again.
The bracket should the derivation should be applied only to Wn plus 1, not to the not.
I was missing a parenthesis. Okay, thank you. Sense?
Yeah, now if you take m.
Okay,
minus
great.
Okay. Thanks. Thanks. Yeah, I mean, okay, so this, yeah. Thank you.
Then, so this analytic continuation argument has no chance of working characteristic P.
Look, I don't know if anything has a chance of working. I mean, I really can't comment intelligibly, but I mean.
No, I mean, you can make sense. It's a divided power derivative.
Yeah, divided powers and so on. I really, I have no idea.
Since I thought about this.
Yeah,
It was vertex algebra, so like C of C instead of C or something. Defining vertex algebra is over like.
Yeah, sorry, when I say analytic continuation, I just mean like say like, when you kind of write out the relevant formula, right? There's something, state field correspondence is appearing here, and this kind of depends on the level, but you just notice that there's kind of no hole when the level goes critical. So it just, I definitely can't comment intelligently on characteristic P because I don't understand the characteristic zero situation at all. So it's just.
Isn't there like proof of the conformal by like normalizing the signal or like element or something?
Yeah. So the conformal structure comes from the Siegel-Seguar
I'm saying
construction.
if you normalize it, you can make it non-zero also, or like make it work a little bit.
I see.
Like that, I think.
Okay. That sounds plausible. Yeah, so I think again, this conformal structure, whatever it is, comes from the Siegel-Seguar construction, and that's something that, well, something very specific happens at critical level and no longer conformal, but this quasi-conformal thing is kind of designed to include things like this at critical level. Okay. Questions? Okay, so let's move on to the construction of Chiral algebras from quasi-conformal vertex algebras. So, I mean, the point of this quasi-conformal business is basically, you sort of equivariant for the action of automorphisms of the formal disk. And so it should kind of make sense. If I have a quasi-conformal vertex algebra, there should be naturally sort of, I should be able to produce them at a vertex algebra on any formal disk, not necessarily with a specified coordinate. That's kind of the point. And in particular, I can do this for kind of the formal disks around all points in a curve simultaneously. So that's going to be the idea of the construction. So again, X is going to be a smooth curve. I'm going to consider the following space called a piece of X. So it's going to consist of pairs X comma Z, where X is a point of X, and Z is a coordinate in the formal completion at that point level X. Coordinate, or if you're a theory inclined, you might say uniformizer, right? Something that generates the maximal ideal here. This, of course, naturally projects to X. And this is a torsor for the group aught 0, where aught 0 is kind of the thing you get by exponentiating air sub 0 I guess more to the point, it's in this description, it corresponds to the condition that A0 equals 0. So it's exactly the reduced locus inside of auto. Okay. Great. So I'll come back to like what's going on with the entire automorphism group, but let me focus on this aught sub 0 for a second. The problem?
An anonymous scribe asked if this notation is consistent with that notation.
Which notation?
There's 0 up in 1b.
Yeah, this is where the 0 plus versus plus that comes up, I guess.
Why? This is exactly baseball preserving. Like this is starting with acting by scalar.
Yeah, but sorry, I think this should have been der plus maybe. Wait, no, sorry.
No, this is
Sorry. So so this, sorry. This was just totally off, right? So this, let me call this der plus. I think that fixes it, right? Sorry, these conditions are obviously not consistent, right? The way I wrote it before. So I really only want to require the quadratic and higher terms to act a little bit.
Oh yeah.
So that's what I'll call der plus.
Yeah.
Okay. Thank you. And I just had a feeling it was screwing something up there. So thanks for pointing that out. Okay.
And der 0 is what you wrote before, without the square.
Yeah, exactly. Yeah. Right. So again, it's the condition that A0 equals 0, whereas der 0, sorry, like aught plus would be the condition that A0 equals 0 and A1 equals 1, right? Okay. Again, this is the underlying reduced locus of aught 0, so it doesn't have this kind of funny nilpotent direction. Okay, and so basically what I'm saying is that if I don't include these nilpotent things and just consider the automorphisms that I think, as Elkanan said, there's sort of automorphisms that fix the point x, right? Technically, there are also these kind of automorphisms that kind of infinitesimally translate x, right? And so aught 0 excludes these, okay? And so this is exactly going to be a torsor, right? Because for aught 0, because this is the same thing as a choice of coordinate is the same thing as an isomorphism of this thing with kind of disk with the coordinate. So select here. It'll act simply transitively on the space of such automorphisms. Okay. So what this torsor does is it allows me to construct from quasi-conformal vertex algebra, or even just something with an action of aught 0 of O, kind of infinite, possibly infinite dimensional vector bundle on X. So V is a quasi-conformal vertex algebra. Really, all I'm going to use here is the fact that aught 0 acts on it as a vector space. I can construct this thing I'll call script V. It's going to be the associated chief right, so I have this torsor for this group. Sorry, that's aught 0. I have the torsor for this group aught 0, px, right? Aught 0 also acts on V. This the whole aught does, right? And so I can attach this torsor px, this representation of aught 0, a quasi-coherent sheaf on X. It's going to be locally free with fiber B. Yeah, because I guess I didn't mention before, another kind of important point is that this torsor is Zariski locally trivial. Just got a little confused about this, but it's like, the point is if you choose an étale coordinate on X, it actually trivializes this torsor over the kind of neighborhood where like an étale coordinate, right, is I have a Zariski open inside of X and I have like an étale map to A1. And a choice of such an étale coordinate will actually trivialize this torsor over that open neighborhood. Okay, great. So this at least gives me, this is going to be the kind of underlying quasi-coherent sheaf of my vertex algebra. So sorry. On the very first thing. Now the next thing I want to do is construct the connection on it, right? Because vertex algebra is supposed to be a D module. Okay. So for this, I'll make the following observation, which is that, in fact, I pointed out aught 0 acts on Px, but by the exact same argument, the entire automorphism group actually acts on Px. Right? If I interpret Px again as kind of a as a functor of points, right? You'll see this thing acting, and the reason I didn't say this before is because it acts, but it doesn't act. The action doesn't respect the projection to X, right? So instead, what happens is that if I take the quotient by this action of the entire automorphism group, if I quotient by aught 0, I get X. If I quotient by the entire automorphism group, I get what's called a Durand stack of X. So X to RAM is the space, its star points are reduced points of X. So it's kind of a funny space. It's not a scheme or anything like that. Okay, but I'll say a little bit more about what this thing is in a second, but just for the moment, first of all, I think this is pretty easy to see from the definitions. Okay, so basically, again, this kind of formal direction is exactly acting by kind of infinitesimal translations in the base, right, in X. So if I mod out by those as well, I'm exactly kind of identifying all kind of infinitesimally close points in X. Okay. So then that means that this V, I can actually descend it by taking the induced sheaf on X to RAM. So all I'm saying is that this additional part of O that is not an aught zero is exactly the datum that allows me to descend this script V to X to RAM. And I claim this is exactly the datum of a connection on script V, on this quasi-coherent sheaf script V. This is an observation of Grothendieck's. Alrighty, if you haven't seen me give a talk, you can see at this point how allergic I am to writing formulas. So it's explained this way. I mean, I think Frenkel BunG V explained the construct of this connection in 2 or 3 different ways, and they do give this explanation in some form. So Grothendieck tells us that to descend a quasi-coherent sheaf from X to X to RAM is precisely the datum of doing a flat connection. Identifying fibers at infinitesimally close points. So I'm just going to kind of take this as an input. So, and sort of the slogan is that the translation operator allows us to define parallel transport on script V. Okay.
Explain a little this IPX mod aught zero. Or O is X to RAM.
Yeah. Think about what the so okay. I'm not going to be able to do it in real time at the board, but I'll just say again, the part of aught that's not an aught zero is exactly a copy of GA hat. Okay, and I claim that copy of GA hat acts kind of simply transitively on spoof of formal power series. So when you mod out by that, you're exactly killing like formal disk. So when you do it here, you're kind of again pushing out such a way that you like. You think about what it takes to descend from X to RAM. Fiber of this projection over an individual point is exactly the formal completion of X at that point. Okay. So when I mod out by this aught zero, I'm exactly killing these formal directions in X. Okay. Does that make sense? Yeah. It's somewhat satisfying? Okay, great. Okay, so far we've constructed the formally a quasi-coherent sheaf, and now we can revise it to saying it's a D module on X. Plan, which I guess I never actually wrote, is that it's going to be able to produce a chiral algebra structure. So the next thing, kind of the most interesting part, is the chiral Lie bracket. Actually, yeah, okay, let me just write this. Do something like this. And maybe this would actually be a good time to break before I do this construction. Okay, so during the break, there was some discussion about left versus right D modules. We decided that, I'm really writing down E as a left D module, but kind of understood in the
Right way.
what?
In the right way.
Well, I would say in the wrong way.
Yeah, okay.
Left D module, like in the kind of classical sense. So, okay. So I'm not saying left D modules I'm wrong. I'm saying like it's a question of whether you include the shift in omega, and it's related to that. So I'm just going to be sloppy about this. Okay, so I'm supposed to construct the chiral Lie bracket. This should take place in D modules on X squared. So I'm not actually going to do this. I'm going to some piece of it and refer you to Frenkel bins V for the actual. I'll kind of characterize it, but won't prove the existence. So so again, sort of consider the underlying quasi-coherent sheaves. Or here I'm thinking about these things as lefty modules. And I'm going to consider the restriction. So again, it's supposed to be, if I forget, then I'm supposed to have a morphism on quasi-coherent sheaves on X squared, and then I'm further going to restrict to the formal completion of X squared at a point in the diagonal. So I guess I could write it like, this. Whether or not I wrote the parentheses, you probably wouldn't get confused, but I mean, it's the completion of X squared at like delta of X, or that's the same thing as this square. Okay. Anyway, you know what I mean? So what I'm going to do is I'm going to actually construct this morphism over this thing, and then kind of as the point X varies, its restriction to all these formal neighborhoods will determine it, sort of because the right-hand side is supported on the formal, is set theoretically supported along the diagonal. Okay. So if I fix a coordinate at my point X, so again, this is for some X. So if I fix a coordinate X, I can write the two sides of this thing, or rather their restriction, as follows: coordinates. So this J lower star, J upper star, V box times V. Restricted to this formal completion. looks like what exactly? It looks like V tensor V power series in two variables, but with the difference of the variables inverted. Right? That's what this J lower star, J upper star operation does. So we're getting closer to kind of vertex algebra language. And yeah, and so I said some kind of cryptic stuff about this Durand direct image earlier. So I'll actually write a formula for it looks like, at least after restricting to this completion, just at the level of the underlying quasi-coherent sheaf, it looks like the power series in two variables with the difference inverted modulo, well, just kind of the principal parts of these things. So this is what this underlying quasi-coherent sheaf of this Durand direct image looks like for a closed embedding. This is kind of what I meant about like it's definitely more complicated than the quasi-coherent sheaf direct image, which would be kind of would be kind of the same size as the structure sheaf on the diagonal. This thing is much bigger. It has kind of infinite dimensional fibers. That's because I have to have kind of all derivatives of this thing in there as well, in order for it to be a D module. Okay, so now I can kind of characterize this power Lie bracket by a formula in terms of the state field correspondence. So this is carried out in detail in Frenkel-Benz chapter 19. So claim is there exists a unique power Lie bracket T, the form I wrote up there, given by the following formula. So it's going to be linear over, in particular, like since it's a morphism of quasi-coherent sheaves, it's going to be linear over functions on this formal completion. And so since J lower star, J upper star is kind of has the form written over there, right? I just need to specify what happens to vectors in V tensor V, and then the kind of rest of it is going to be determined by this linearity. So I just need to specify what it does to vectors of this form. So it's going to be given by following formula. Where, if I'm not mistaken, this makes sense because of the locality axiom. Saying some nonsense, or does that?
Probably.
Probably. Well, I mean, I need this to be actually a Laurent, like that finite number of.
This is like, what does it mean to be a field?
Yeah.
Locality is the commutator. This
has to do with the order of the pole in Z minus W. So it's saying when I like multiply by it, yeah. And I mean, this kind of, there's other ways I could write this formula, but okay, it's a. I'll just reveal my ignorance if I say more, but I say that this formula is well defined.
No, you're correct. Use locality.
Use locality to make sure this is well defined. Okay, that's what I thought. Okay.
Yeah, and this doesn't need anything about commutator. Just field means that every object is in Laurent series.
It's really just because it's a field.
It's just a matter of name. Do we call that locality or do we call that definition of field? Yeah, we need the fact that it is a Laurent series.
No, yeah, we need the fact that this is a Laurent series in Z minus W. That's okay. Whatever axiom ensures that, that's what I'm using here. And again, this bracket, I think at the level of, well, yeah, it's determined, right? This chiral bracket is certainly determined by the fact that, right, this formula, it's given by this formula over all these formal completions. Any point. And again, that's because the right-hand side is kind of set theoretically supported along the diagonal. So the bracket is determined by what happens, when I take the underlying quasi-coherent sheaves and restrict the formal neighborhood of the diagonal, and then I'm kind of further restricting the individual points. You could also do something like this kind of in families as the point x varies, but in any case, look at Frenkel-Binsby chapter 19 for the details. So there's many things being asserted here, right? One is that, this actually defines a morphism of quasi-coherent sheaves over x squared. Another is that it's compatible with the connection on x squared. Another is that it's actually a chiral Lie bracket, right? So all these things are checked there from the vertex algebra axioms and the quasi-conformal structure. And yeah, so that's the chiral Lie bracket. So somehow the state field correspondence exactly allows us to write down this chiral Lie bracket. And there's also going to be, it's actually going to be a unital chiral algebra. So unsurprisingly, that comes from the backing vector, right? So I have the backing vector inside of V. This is a morphism of vertex algebras, in fact, and so I'll get morphism of chiral algebras like so. Again, one has to check this satisfies the unit axiom, which is done in Frenkel-Binsby chapter 19. Okay. Other questions? This is okay? All right, I'm not giving a lot of details, but I would, trust me, you wouldn't want me to. It's explained very nicely in Frenkel-Binsby, so take a look at that.
And here.
Okay, so not all chiral algebras arise in this way. Now, you can already see this, right, from the way that I wrote down the underlying D module or even the underlying quasi-coherent sheaf of the chiral algebra is a very particular kind of thing, right? It's like an infinite rank vector bundle on X, and certainly not all chiral algebras don't have to have this form. So the ones that do are what's called universal, meaning they're not really attached to a particular curve. My choice of X was incidental. It's just, I can do this clearly, well, what I mean to say is my X was arbitrary, right? So I could carry out this construction for any X, and the chiral algebras I obtain will be compatible under pullback. So if I have any étale map, generally chiral algebras will at least pull back nicely under étale maps. So if I have any étale map of curves F from X to Y, and I can sort of carry out this construction on Y, and then I can pull back along F. And this will naturally identify with the construction carried out on X. Okay, and so I think one can prove some kind of equivalence along these lines, that these things are exactly equivalent to quasi-conformal vertex algebras. I didn't look super hard to see if it's actually written Frenkel-Binsby, maybe. This seems to be kind of folklore. One can imagine, right, if you had a chiral Lie bracket, like trying to write down a state field correspondence by restricting. And okay, so that's everything I have to say about this construction. Questions? All right. So I'm going to be able to say everything that say. I guess what I'll do now is I'll discuss Feigin-Frenkel at critical level, and then I'll come back and talk about factorization algebras such if there's time. So I think for kind of the purposes of this seminar, Feigin-Frenkel stuff is more relevant. So. This is about chiral algebras is kind of relevant to what I'm about to say. So maybe these two parts are kind of disconnected. Great. So last week we talked about the Feigin-Frenkel isomorphism. It's this kind of isomorphism of W algebras for attached to Langlands duality algebras at dual levels. And the proof is this really funny thing where we proved it kind of generically and then somehow can deduce it for other levels. So critical level is very special. So I'm not super clear, I guess, on like the relationship between what I'm about to say and last week. So maybe it'll become more clear and people can help me clear this up. So first of all, I have any vertex algebra V. There's a notion of its center. So the level of vector spaces, the state vectors will consist of those vectors in V such that this equation is satisfied. I think from the discussion about commutative vertex algebras, hopefully it's believable that this is like the correct analog of centrality, right? And you can also write this as like the kind of field attached to A and the field attached to B with two different variables. We'll commute it zero. Right that. So this is a commutative vertex subalgebra B. One can check. I'll smell gas.
Yeah.
Okay. Not good. Still not having a stroke.
Oh, yeah.
Yes.
But I guess
Oh yeah, I guess it does work. I have no idea.
Yeah, I don't know where the guest.
We open the web.
Okay.
I'm smelling it.
If someone passes out, we'll notice it. So no, crack a window, sure. All right. So I'm gonna talk about this Kac-Moody vertex algebra where there's this dependence on a level, which was a invariant bilinear form on the Lie algebra. And there's a very special level called the critical level, right, which is -1/2 times the killing form, sort of a distinguished canonical level. Turns out -1/2 of it is the really important one. Okay. And first thing, oh yeah, by the way, another good source for this material is Frankel's book, Langlands Correspondence for Loop Groups. Has some really nice discussion of the critical level situation. Okay, so in particular, it proves like I think everything I'll say today. So for non-critical level, turns out that the center is trivial. It's as small as it can be, which is to say it's easy to see the vacuum vector is always in the center, and that's for non-critical level, that's everything. Okay, but at critical level, it's turns out to have this huge center. So first, I can describe this center in slightly different terms. So I can check that this center kind of, okay, first at arbitrary level is identified with the subspace of invariant vectors for, so this thing is, by construction, is a representation of the Kac-Moody-Lie algebra, and you can check that this condition is equivalent to being invariant under the action of the Kac-Moody-Lie algebra. Oh, sorry, that's wrong. Sorry, it's supposed to be, sorry, it's, what do we call this? G sub O or something like that? Plus G, okay. Sorry, that looks better, right? Sorry, it's the invariant vectors for the positive part, the loops of G. Another way of writing that, again, this is the, morally up to this twisting business is like the induced representation where I take the trivial representation of arcs of G and induce to loops of G, right? There's this twist, which I'll ignore. And this is endomorphisms in Kac-Moody representations of the vacuum representation, right? Hom out of the vacuum representation exactly takes invariance for the arc group, again, because it's this induced representation. And so this is this endomorphism algebra. And so I claim that you have this isomorphism as associative algebras, which are, we know kind of, because of the left-hand side, are actually commutative. So what am I saying here? So first of all, if I have a commutative vertex algebra, as previously discussed, that actually defines just a commutative algebra structure in the usual sense on it, right? And so if I view this thing as a commutative algebra in the usual sense, saying this is an isomorphism of associative algebras, this thing is an associative algebra by virtue of being endomorphisms of something. It's not at all obvious that it's commutative, but that turns out to be, well, sorry. Easy. That turns out to be the case after the fact. Okay, so this is for arbitrary level. And level will remain arbitrary for a little bit longer. So also,
this looks a lot like Sergal's endomorphism sets theorem. Endomorphism of the vector, the center.
Well, that's the endomorphism projective is, it's not the center, right? It's the kind of co-invariant algebra of the center of the model group.
Well, yes, with the W lambda invariance of the center, but when lambda
is commutative in particular.
Yeah,
although that's like.
But exactly what you said, like the fact that the endomorphism algebra is commutative is surprising. It's proof because.
Yeah, but again, I would say in that situation in category O, it's not really a commutative situation. Like the big projective doesn't generate the category O, right? You have to take projective covers of all objects, and if I take endomorphisms of that thing, it'll be non-abelian. This is definitely a more commutative kind of situation because it's more like the kind of Whittaker category in the finite dimensional situation.
Is the Kac-Moody algebra projective as a module over GK?
This thing, it's a projective module, probably not.
That's not classical.
Yeah, this algebra is not classical. Yeah, sorry. So here I really mean classical. Yeah, in fact, that's a good point. Very good point. Thank you. Very important that I'm taking the classical endomorphisms here because there are X's, and as a derived algebra, like the actual R endomorphisms is non-commutative as a DG algebra. So.
What it is? Done explicit description of the whole thing.
Well, yeah, because we kind of know. I mean, you can describe it in terms of opers, a posteriori, but it looks like the self-intersection of the kind of locus of regular opers inside of all opers or something like that. That thing is like it's a groupoid, and you can convolve sheaves on it, but it's not going to be commutative. Okay. So last time and before that, I guess 2 lectures ago, we defined this functor of Drinfeld-Sokolov reduction. So if I have a representation of this Kac-Moody algebra, there's this kind of fancy twisted semi-infinite cohomology operation, right? Where I sort of take semi-infinite cohomology against this non-degenerate character. Was it called Drinfeld-Sokolov reduction actually in the? So it's you know, semi-infinite. It is due to Drinfeld and Sokolov, or at least it's usually attributed to them. So it's sort of the semi-infinite Vickers reduction. Okay. Previously, I mean, this is the thing that we used to produce the affine W algebra by applying this to the vacuum, right? And so the reason I'm writing this as a functor is because the center of the vacuum representation, again, because it's endomorphisms of the vacuum representation, it therefore acts by functoriality on Drinfeld-Sokolov of the vacuum representation. By functoriality. And using that identification. And remember, this was like by definition, this was the W algebra attached to affine attached to this Kac-Moody algebra. Principal one, of course. Okay, so we get an action of the center on this W algebra. I should say, like, if you think about this in terms of, you really should, be thinking about these as DG categories, and this is some like really crazy, like super derived thing, but it just so happens that this is like a classical thing that's like really lives in cohomological degree 0, and that was kind of a miracle. So just to emphasize. Okay, so, okay, and then inside of the this W algebra, right, we have the vacuum vector. So we previously saw, right, that this thing actually has a structure of vertex algebra. In particular, it has this vacuum vector. It's easy to see from the construction when you write it down explicitly. And so in particular, I get a map of vector spaces from this center to the W algebra, which is act on vacuum. Right. The module, I specify a vector, and so I can act on it and I get a map. Call this star. Okay, and then the big theorem here so this is all to do with Feigin-Frenkel, is that if kappa is critical, then star is actually an isomorphism. This is definitely specific to the critical case, right? And you can actually prove that it's an isomorphism of quasi-conformal vertex algebra. So it respects the vertex algebra structures, and it also respects the action of derivations of O. Notice this is somehow exactly analogous to what happened in the finite dimensional situation, right? Where the center identified with the finite W algebra, principal W algebra in exactly this kind of way, right? But in the affine situation, it's very specific to the critical level situation. Notice away from critical level, I wrote right there that this thing is trivial, right? Whereas this thing is interesting and non-trivial even away from.
Generically, it's still the same. Something generically, F and W algebra was what?
No, it's not trivial generically, right?
It's not trivial, but it's like generically all the same.
I thought it was that it was generically all the same, like as a. Is it generically the same as a vertex algebra, or just kind of as a vector space? Yeah, like this.
Oh, okay.
Same as a vector space, but the vertex algebra structure surely is varying, right?
Okay,
Yeah.
Not a derived theorem, right? Like you said. The
Yeah,
left
yeah, this
hand
is
side
kind of-
very derived, and the right hand side is not.
I mean, again, this was like this thing. Even if you interpret this thing derivatively, it turns out to be classical,
Yeah.
right? Whereas this thing, I sort of, in order to define it, I had to like make the construction classically and say it was the classical center. If I do kind of the derived center, I'll instead get something that looks like Hochschild cohomology or something. It'll be something derived and generally non-commutative. But the same is true in the finite dimensional case. It's like the I take like okay, yeah. So maybe it's instructive to think about the finite dimensional case, right? If I take endomorphisms of the enveloping algebra as a bimodule over itself, right? Classically, that gives you the center, but derivatively, that gives you Hochschild homology, right? And that'll be a non-commutative DG algebra in general. So it's very much analogous here. So I'm taking really the classical center. That part is commutative. The derived thing is not, and I don't have anything to say about it.
So you said this is for the principal case. Is there a Feigin-Frenkel duality, isomorphism?
Remember, I asked Losev this at the end of his talk. I said, yeah. So
really? Oh,
yeah.
Oh, okay.
He said he's doing some calculations of W algebras in the non-principal affine case, and I asked if it was related to Langlands duality, and he said no.
And this is called Langlands duality.
Well, it's oh, sorry. So I guess there's no Langlands duality appearing this stage. So
I'm just asking if you can identify like affine W algebra away from principal case to like some sort of center.
oh, I have no idea, but probably not, because again, in the finite dimensional case, you can't do this, right? I mean, well, in the finite dimensional case, the W algebra is non-commutative from the principal case, so probably even at critical level, that's probably also true in the affine case.
Okay.
Right. Yeah. So that's a good point. Langlands duality has not actually appeared. What I'm about to say is probably logically out of order, or not the way that Feigin-Frenkel actually proved it, but the thing I say is at least true. Okay, and then as a corollary, yeah, now we'll introduce Langlands duality by invoking the Feigin-Frenkel duality from last time. So corollary, and maybe what I'm about to say is kind of silly, so you can tell me. Is that this center at critical level is canonically isomorphic to functions on opers on the disk, stool group. And here Langlands duality is appearing. So this thing on the right-hand side is defined last time, again, as quasi-conformal vertex algebras. Commutative. And okay, again, this is where I'm saying probably the logic is all screwed up, so tell me if this is. So my impression is that kind of, so first of all, there was this discussion last time of lack thereof of dual level, right? And whatever this duality operation on levels is, it should exactly interchange the critical level and the. So you should think like, if my Lie algebra is simple, so the level is basically a number, This duality is like 1 over kappa plus a half. That's right, where it normalized by using the Killing form. So it'll go critical level to infinity. And then Feigin-Frenkel tells us that the W algebra at critical level identifies with the W algebra for the duality algebra. Sorry, don't. Okay. This looks okay. So probably, yeah, this is just totally goofy. So I should say something like maybe I should write it instead like this or something. It's the kind of W algebra at level infinity, and Kevin explained last time that this is. So I sense that this is function fun. This looks kind of familiar from last time. There was this discussion, right? And so I think this makes sense. But if you look in Frankel's book, the loop groups, Langlands correspondence for loop groups book, I don't think he ever actually mentions W algebras there. Instead, he kind of proves this identification directly. So it's possible the logic is just totally goofy here, and instead you first prove this, and then you use that to deduce Feigin-Frenkel duality at critical level. But in any case, all of the isomorphisms I've written are true. It just a silly way to arrange things logically.
Wait, first isomorphism said that's Feigin-Frenkel or FF duality?
Feigin-Frenkel duality, yeah.
I thought that was last time.
Yeah, it was.
So both of these are last time.
Yeah.
Both.
Just check. Yeah, this right. Feigin-Frenkel duality from last time, and then also in the course of that proof, right, there was this argument that the W algebra level infinity kind of naturally identifies with functions on regular opers. Notice, like here, this is G, the W algebra for G check at level infinity. So the group here are the same. And the Langlands duality happened in Feigin-Frenkel duality as it should.
Okay.
So again, it's possible that this is really silly and you should instead first make this identification and then use that to prove this one, but okay. So again, to summarize, there's sort of two different things going on here. One is the fact that the W algebra at critical level identifies with the Feigin-Frenkel center, and the other is that the Feigin-Frenkel center is canonically functions on opers. Two important things. Okay. I think that's all I have to say about Feigin-Frenkel at critical level. Questions?
Enter trivial also in the derived sense outside of critical level?
Probably. Should be an answerable kind of question. So. I think so, right? So at least generically, I'm not so sure about integral level. So, okay, so the kind of Kazhdan-Lustig category, the like L plus G integrable Kac-Moody representations, this FLE away from critical level is going to identify that category with Whittaker D modules on the affine Grassmannian with kind of for the dual group with a dual twist. Okay. And the vacuum will correspond to kind of the vacuum Whittaker sheaf. And so again, it should be at least, yeah, and actually probably at all levels by kind of a cleanness argument, anamorphisms will just be trivial derivably. So if you use only at arbitrary levels, which is known, well, it's a paper by me, Sam Raskin, and Gerber Dillon. Although it's sort of at a point, so it doesn't kind of reckon with the vertex algebra structures, but at least like as it's a statement about associative algebras. Yeah, of course, This kind of thing doesn't. Yeah.
So now you'll tell what FLE.
Yeah, I guess so. So, well, okay. So my plan was I was supposed to talk about factorization algebras as well, and I certainly can't really talk about FLE without. So I guess there's sort of two things I can do. I could either spend the next 15 minutes explaining the connection to factorization algebras, or I could assume the connection to factorization algebras and talk about FLE, which is a better sort of second option. Okay, assume something there. Okay, so
notes, right?
Do that. Saw several votes for the second option, so I mean, there's no way I have time to like kind of systematically. I interpreted that correctly.
Yeah.
Okay.
No, you
Just wanted to make sure I'm not.
Sorry.
You explain in your notes the connection, right?
Yeah, it's actually written in the notes, so there's something, and I mean, but yeah, it's not. I'm not saying it's well explained.
Let's see this. Like,
it's in there. Okay, so, and I mean, again, it's I have to use things that I wouldn't have time to explain regardless, so it's going to be a little bit more loose. Yeah, this is not in my notes, so this is going to be kind of freestyled. So, great. Okay, so so we had this discussion about chiral algebras, and I guess I should say technically, I'm about to say non-unital chiral algebras are equivalent to this other kind of object called the factorization algebra. There's this other kind of structure. It basically just means so. Factorization algebra structure means I have a D module on Ron space, where Ron is the moduli of finite subsets of X. And Ron comes with this operation of union. And I can also consider just those pairs of subsets that are disjoint from one another. Call that inclusion J. So the factorization algebra structure looks like say it correctly. Yeah. Morphisms like this over Ron times Ron disjoint, satisfying some commutativity and associativity conditions. So if I have a collection of disjoint points, the fiber of the factorization algebra just looks like the tensor product of the fibers at those individual points, but the non-trivial structure is really encoded by its structure as a D module on Ron space, where these kind of families of disjoint points are allowed to collide in one kind of where the trivial information is. Okay. And so the construction to go from a chiral algebra to a factorization algebra is a it's really a Chevrolet complex. So somehow there's a causal duality between these two things. Yeah. Reference for this is a paper by Francis and Gatescory. Okay, so the benefit of factorization algebras is that they are amenable to geometric constructions in a way that these other objects are not so much. And it's really, I mean, if you kind of want to get the explanation for why that is, this factorization structure is somehow some kind of commutative algebra or co-commutative coalgebra structure. And so it's really commutative algebras that are directly connected with geometry. Okay, so there's also notion of factorization categories. Okay, which, yeah, again, really don't have time to go into details, but it's a similar kind of datum. It's like somehow I have a crystal of categories over the Ron space with exactly this type of structure. And you should think a prototypical example would be the following kind of thing. So there are many examples of what are called factorization spaces in nature. So maybe this is sort of a nonlinear version of the definition of a factorization algebra I just gave. And these are, what makes it a factorization space is that we have exactly this type of structure, level of spaces, right? So if I base change to Ron times Ron disjoint, it factorizes example, the valence and Drenfeld affine Grassmannian. And you should think that the way I produce factorization categories is by taking categories of sheaves on factorization spaces. And then factorization algebras will kind of typically arise from sheaves on these kinds of factorization spaces, either just as such, like for example, the kind of unit object in here, I can think of it as a factorization algebra in this factorization category, or by applying some constructions to it. So I could also do like global sections of, I could take distributions on a factorization space or something like that, and it would produce a factorization algebra. So these are typical kinds of examples. And okay, perfect. So I was going to use this. So the Drenfeld-Sokolov reduction. So first of all, I want to say that this is naturally has a structure of factorization category. And really the reason is because factorization spaces tend to arise by certain constructions attached to disks or formal disks. So for example, loop spaces, arc spaces, things of that nature. Because I can make sense of loops and arcs kind of in families and talk about multi-disks, this sort of thing, right, all over the Ron space, I can put factorization structures on like loops into something reasonable, like the group, for example. And so that means things like the affine Grassmannian have factorization structures. Similarly, that this looks basically like loops into the Lie algebra. So therefore, it'll also have a factorization structure. So this is going to be compatible with the structure. So if I have kind of a factorization algebra in here, for example, and I apply Drenfeld-Sokolov reduction to it, it'll spit out a factorization algebra in vect, which is just a usual factorization algebra. So this tells us, for example, if I take this vacuum representation, again, because it was something that was just kind of attached to the disk and the formal disk, right, by this induction procedure, this also naturally factorizes. And this factorization algebra structure I mean, I could also forget the fact that it was an object of this category and just view it as a plain factorization algebra. And that structure exactly corresponds to the vertex algebra structure on this thing that we've been considering under this dictionary action. But here it's kind of coming from geometry. Basically out of time, so let me just kind of very quickly explain the construction. So this is in proof of geometric Langlands conjecture, the second paper, something Kac-Moody localization and something. There's FLE in the title as well. Okay. So what we do is we consider this Drinfeld-Sokolov reduction construction as a functor from Kac-Moody representations. Now I'm going to specialize to critical level. Instead of writing kappa crit, let me just write just crit. And then I consider the ones that are integrable for the art group. Okay, so this is sometimes called the Kazhdan-Lustig category. It's like you could think of it, if you think of this as some kind of like maximal parahoric subgroup or something, this is somehow analogous to category O, finite dimensional case. Okay, anyway, and then I have this Drinfeld-Sokolov reduction. Okay, and Feigin-Frenkel told us, so first of all, this vacuum representation lives inside of here. This is certainly integrable for the art group because it was kind of induced from the trivial representation of the art group, right? And Feigin-Frenkel told us that this maps to exactly functions on Opers, the Langlands dual group. And again, look, it's attached to the disk. This is also a factorization algebra, but it's a nice kind of factorization algebra because it's commutative. So it's really kind of anytime I have a factorization space that's really attached to the disk, as opposed to the puncture disk, just the disk, and I take functions on it, it'll have this kind of commutative factorization algebra structure. And Feigin-Frenkel, because it was supposed to be compatible with the kind of quasi-conformal vertex algebra structure, tells me that this guy maps to this guy really as factorization algebras. Okay. And so what this does, well, so okay, so this is ingredient number one. But I actually need a slightly upgraded version of this. So now I need to use geometric Satake. So write spherical category of G for spherical Hecke category. This is exactly the kind of universal thing that acts whenever I have a category acted on by loops of G and I take L plus G invariance, it's going to act. And so this will act on this Kazhdan-Lustig category. I guess I should say critically twisted. Everything at critical level here. Okay, and geometric Satake is a monoidal functor from representations of the Langlands dual group into the spherical category. And so in particular, it follows that rep G check acts on the Kazhdan-Lustig category. And I want to say that this Feigin-Frenkel isomorphism has a further compatibility, which is a compatibility with geometric Satake. Okay. Because I didn't really prepare this part, I'll probably fail to say. I guess I can say it. So let me try. What is the compatibility of Feigin-Frenkel at critical level at geometric Satake? This is sometimes, I guess, in Balance and Drinfeld's book on construction of Hackett eigensheaves. It was called the birth of Oper's construction. Okay, so the center, of course, acts on the vacuum representation. Okay, and so this gives us a functor from just modules over the center, just usual like left modules, just thinking of it as a commutative algebra, right? Into the Cauchy-Lustig category. Which is like, if I have a module, right? Since this algebra, commutative algebra acts on this particular object, I can tensor the module, right? Tensor over Z with that module, and that produces a functor like this. And the compatibility is that, well, so this thing we said is equivalent to functions on Opers. Opers on the disk is an affine scheme. So this is actually just equivalent to quasi-coherent sheaves on Opers. Right, so this is a more categorical way of saying the Feigin-Frenkel isomorphism. And then this thing is acted upon by ref G check because, well, I can also think of this as quasi-coherent sheaves on local systems on the disk. And if I have a G-check Oper, it has an underlying G-check local system, right? So there's a projection in this direction, and therefore inverse image of quasi-coherent sheaves defines a symmetric monodal functor like so. So ref G-check actually maps symmetric monodally here, and in particular it acts. And so this compatibility that I was speaking of is equivariance of this functor for the action of Satake. You could write it definitely much more explicitly than I did. This is just the only way I could reconstruct it, but there's a kind of explicit like eigenproperty for the action of Satake that you can write this way. Okay, but now, like once you know all of this, you're basically very close to just understanding the Cauchy-Lustig category at critical level completely, because what happens here is like Cauchy-Lustig category is really generated by the vacuum representation together with kind of what I get by acting by any finite dimensional or any irreducible, say, G-check representation on the vacuum. Those are going to generate everything. And so if I kind of understand this action and I understand, you know, I have this Drinfeld-Sokolov reduction that goes to Opers, functions on Opers, then very close to being able to just describe the entire Cauchy-Lustig category. So here it goes. So first of all, this business tells me that Drinfeld-Sokolov, I can upgrade it. So instead of taking values in vector spaces, I can make it take values in G-check representations. How do I do this? Well, G-check, it's just because ref G-check acts here, basically, right? So basically, I can act by a G-check representation on an object of the Cauchy-Lustig category and then apply Drinfeld-Sokolov. That gives me a pairing between these two categories. And then I use the fact that this category is self-dual to kind of move it to the right side. So you could write some formula for this in terms of like Innerhalm or something, but it just follows very formally from the fact that this is self-dual and it acts. And then this upgraded, or this compatibility of Feigin-Frenkel with geometric Satake exactly tells me that the vacuum representation maps to functions on the kind of universal. So what is this G-check tilde? So I have this. This is really just the classifying stack twice. So I have this thing that classifies the trivial representation, and this thing is the. It's a G-check bundle over Opers. It's this kind of universal thing. So it's a G-check bundle. So this thing is a representation of G-check. Its G-check invariance is the original functions on Opers, but this is some equivariant version of Feigin-Frenkel. Yeah. Makes sense. So hopefully you unwind all the formalities. This is more or less equivalent to what I wrote up there. I'm almost done. Okay, so finally, is that I can further enhance Strand-Valentine laws. So, okay, so this vacuum representation, it's not just any factorization algebra in here. It's actually the unit factorization algebra for the factorization structure on this category. And so I get a functor from this category to factorization modules for whatever its value on the unit is, just by functoriality of the factorization structure. The fact that this is compatible with factorization. And so this is going to upgrade to functor valued in factorization modules for this gadget in reptcheck. This is just some abstract nonsense, just using the fact that this thing is the unit on the left-hand side. So factorization modules for this thing in this category is just this category again, and using functoriality. And this thing I claim is approximately the following. It's more or less those meromorphic opers whose underlying local system is regular. So there's some kind of general yoga of factorization modules for commutative factorization algebras that allows you to kind of write formulas, kind of geometric formulas for categories of factorization modules of this nature. And then this is like approximately an equivalence up to some renormalization. So that you might have to kind of, this thing could be kind of problematic, might not necessarily be compactly generated. These same kind of issues we were talking about previously with this category, right? This category could suffer from the same issues a priori. So you do have to renormalize it, but once you've done this, this will become an equivalence. And so you get Ashton-Lustig is equivalent to, sometimes this is called unramified opers. It's those meromorphic opers whose underlying local system is regular. So that's FLE. Critical level. So obviously that was very sketchy, but do the indication. And again, you see this, I'm really like relying on this factorization formalism in a very heavy way here, right? So that gives you a sense of the usefulness of it. By the way, once you've constructed this functor, there are a couple ways to prove it, but one way is basically to kind of use some formal stuff to prove that, reduce to the case of proving that this is just an equivalence like at a fixed point of the curve. And then this is basically proved by Frenkel and Gatescore in some of their older papers. So I should say this is, if you consider this as like kind of a pointwise equivalence, this is actually, as I said, it was not too far from just knowing Feigin-Frenkel equivariantly, but to kind of prove it as an equivalence of factorization categories is something much stronger. All right, so that was like completely something completely different, right, from like everything else in the seminar. So I hope it was a nice little diversion, but we'll see where things go from here. Okay. I'll stop there.
So how do you describe like fully iterable representation in terms of
And so that would be, sorry, so should have some description in these terms, right? Like the hacker category, exactly. It kind of feels like it would just be completing meromorphic opers along unramified opers, but I thought that that would actually just give you unramified opers again, right? So saying something silly. So yeah, that's right. That can't be right. So like
Particular, what happens if you take just like instead of completing, just taking everything granular?
oh, and taking everything regular? No, that would not be. Yeah. So like what you're doing is like the Hecke category acts here, and taking fully integrable representations would be taking kind of invariance for the Hecke category acting, right? And we know what the action of the Hecke category looks like over here. Namely, it's like loxus on D times loxus on D over loxus on puncture disk, right? Kind of acts by convolutions on this thing. When you take invariance, again, I think it actually should just produce like completion. Feels like it should just produce this. Somehow I thought this was already equal to unramified opers, so now I'm confused. You're right. Certainly would be a reasonable answer, and I'm kind of oh, sorry, no. Yeah, I think this is the correct answer, and yeah, it's not unramified oper. Like the unramified opers mapping to meromorphic opers is an end-closed embedding, but that doesn't mean that it's not like formally a towel or anything. So it's just yeah. So I think this is quasi-co on this thing would be formal completion of meromorphic opers along unramified opers.
I think just
Thanks.